Hey, so welcome everyone. It's a pleasure to have Mina here with us today. He'll be talking about the power of interactive proofs for learning.
Thanks for inviting me and thanks for having me to give a talk. So this is joint work with Tom Gur, Mohammad Jahanara, Mohammad Khudawande, Bahar Salamatian, and Igor Shinkar. Let me just start with just so everyone's on the same page. I'll just explain what I mean by learning here. So we talk about binary classification, where the examples are points in 0, 1 to the n, and they get binary labels 0 or 1, as you can see from my drawings for dog and cat here. And so there is an unknown target. In this case, the set of the target class is the class of hyperplanes, and there is an unknown target which classifies the underlying data set as 0 or 1. And now the learning task is such that you're given examples from some fixed but unknown underlying distributions. And the goal of this task is to output a hypothesis which approximates the unknown target very well. So what I mean to say by approximating the target very well is that the error between your hypothesis and the unknown target is at most epsilon with respect to the underlying distribution D. Now I've said a bunch of things, so I'll try to make this more formal in the definition of PAC learning, but also please feel free to stop me if there's any questions about anything. So this is formalized in the PAC learning model by Valiant, and we say that a class C is epsilon delta PAC learnable from random examples using a hypothesis class H, which could or could not be C itself. If there exists a learner which gets examples from some fixed but unknown underlying distribution, or 0, 1 to the n, and for any such distribution or any such or any unknown target, so the learner takes random examples of the form x, c of x, which is just example and label from the unknown label or unknown target according to the distribution D, and throws out a hypothesis with probability at least 1 minus delta, such that the error of the hypothesis with respect to the unknown target is at most epsilon. And this is called as the random example oracle. So moving on. So we also think about learning using a much more powerful form of access, which is using membership queries. Here, in addition to the random example oracle, your learning algorithm also has access to some boundary points, the data set. And yeah, this seems more powerful than random examples, even by just by thinking about it, even intuitively, because if you want to query some boundary point, the probability that you get using the random examples is quite low, but here you can actually probe certain things. But you also give the learner access to random examples from distribution, because you want the learner to still know something about the distribution itself, where it is coming from. And now again, the task remains the same, to output a hypothesis which approximates the unknown target very well, up to an error at most epsilon with respect to the underlying distribution. Yeah.
What do you mean with boundary points?
Oh, I mean, boundary points is just just an example. It's just some point.
Interesting point.
Interesting
Points.
Okay.
Yeah.
Okay.
There's a technical question. Do you want this drawing bar on the top and the video on the left? Do you want to just go full screen?
Oh yes, I can move this here. This is better.
On the view, maybe be full screen.
Okay, let's try. Is this better?
Yeah, I was thinking about getting rid of the video completely.
Oh, you mean the Zoom? Ah, that's me. That's not him. Sorry.
Oh, that's maybe.
Yeah.
Get it.
Um,
Side-by-side speaker would be perfect.
this one.
Or
I
just
just-
full screen, or whatever. Side-by-side speaker.
That's the one we have. Yeah.
The standard.
Hide.
The standard, you get this, and then I can minimize. Okay.
Fantastic.
Shall I move on?
And we know, do we know separation between, like, if you can do query or not?
Yeah, the formal separations, although this is based on the existence of one-way functions.
Ah, okay.
Yeah, based on one-way functions, yeah, and the realizable learning, which is this, like, yeah, there exist concept classes which you can learn easily using membership queries, but cannot be learned in polynomial time using random examples. So there's like,
And when we say PAC-learn, we want the algorithm, like, are we measuring the number of samples, or we actually want like an explicit polynomial time algorithm? Because
So
you could measure like information theoretically or actually.
yeah, I mean, you can think about it both ways. Yeah, like I'll get to that.
Okay.
As we go through the talk as to what we care about. Yeah. Yeah, this is just like a definition of the model itself. Yeah. And yeah, one of the main goals of the field of learning theory is like what classes are learnable efficiently. One could talk about samples or running time, or both. And yeah, typically when you mean efficiently with respect to running time, say you'd say running time polynomial in n, which is a dimension of the data set, and the size of the underlying concept, 1 over epsilon, 1 over delta. And so for the purpose of this talk, we will focus on the fact that D is just a uniform distribution, which means that your learner only has to work for the uniform distribution. That's the guarantee we need. Yeah. And one more focus of this talk is going to be on the much more general setting of agnostic learning. So here, the underlying function is arbitrary. So to understand the difference between this and the previous setting, which is called as a realizable setting, is that there is a ground truth about the unknown target that comes from this fixed class C. Whereas in this case, there's no such guarantees. So this underlying function, which gives the labels, could be anything. But now, since there's no ground truth which is given to you, you just assume your own ground truth. You just, like as a learner, you've seen like many data sets being classified using hyperplanes. So I'll just say, okay, fine, I'm going to think about hyperplanes for this. This is what I believe is the right measure for this. But you could be very, very wrong. So in this sense, the learning task here is to produce a hypothesis, which is whose error is as close as possible to the best I can produce from a hyperplane. Yeah, does that make sense? Mm-hmm. Yeah. So in this case, agnostic learning. So yeah, you have an arbitrary function, and you have again a random example oracle and a membership query oracle to F. And the goal of the learning task is to output a hypothesis which approximates the underlying function to the best possible it can with respect to the underlying class C. And what do I mean by opt? It's the minimum value over all functions in C, which produces the best possible approximation with respect to the underlying function. And you just want to produce something which is best possible approximation plus epsilon. Yeah.
Yeah, I don't know if this is a stupid question, but is it clear that this additive thing is what you want, or would you would consider opt times 1 plus epsilon or something? Because now you're somehow, regardless of whether, you know, I might be, if I'm very, very close to being realizable, or whether like the concept class is just super crappy, you're somehow still having exactly the same additive shit.
So there's also notions of multiplicative approximation. Yeah, I don't know about 1 plus epsilon. It hasn't cropped up in too many places as far as I know. But typically, because like one reason for this is in the realizable setting, opt is just 0. So in that sense, it directly generalizes, right? So it's 0 plus epsilon. So maybe that's one of the reasons why it's considered opt plus epsilon. So it generalizes multiple known things, yeah. But there's also versions of multiplicative approximations in agnostic learning. And yeah, as I just mentioned, in the realizable case where the underlying function or the underlying unknown target is from fixed class C, then opt is 0. And moreover, this agnostic learning is even more general. So here we fixed like an arbitrary function f, but agnostic learning can also be over joint distributions themselves. Like there doesn't need to be a function which labels the examples. It can just be like you can have the same example having 2 different labels, and yet you want to approximate well. This is just as an aside to mention agnostic learning is considered as one of the more general forms of learning itself. And if like agnostic learning is clear, then I'll move on to the setting where we work with, which is delegation. So now I want to agnostically learn this class C or the uniform distribution, but I have this really old laptop, like it's from 12 years old laptop, which only has random example access. And now I'm going to delegate this task of agnostic learning to this big, powerful server out there who has more resources and possibly has better access to the function as we're using membership queries, and who claims that they can output a good hypothesis to me. And sure, like, so I'll just delegate the task to the learner and receive the hypothesis back, and all good and done. But I don't trust the server out there. So it could be this server who's actually claiming to learn and giving me a good hypothesis. But on the other hand, it could be like someone sitting in the basement sending me like a really poor hypothesis. And I still need to be able to check if the results of their computation is correct or not. So what I do is I place the burden on the learner to prove to me that they have accurately learned this, agnostically learned this class C. And yet I want to check this using as few random examples as I can. So there's a notion of delegating agnostic learning. And
sorry, so the random examples are like your own laptop has access to random examples, but you don't use those to learn.
Yes,
the powerful learner will give you the hypothesis. You use them to check.
To verify. Yeah. That's exactly like the verification setting for like learning itself.
Yes.
But my old laptop cannot probe like that.
Yeah, old laptop cannot probe.
And there's a reason for this.
I mean, it can. Okay, again, once we get into formal details, I'll explain. This is again trying
We
to.
are 2 slides ahead of you.
Yeah. I'll get there. Yeah. So a very natural way of dealing with this is via interactive proof systems. So just taking a step back, like forgetting everything about learning. So interactive proof systems, which all of us know about, but I'll just briefly mention. So you have an input X to the language L, and you want to decide if it belongs to the language or not. And now you have a verifier, which is like a polynomial time verifier. And then there's a prover who's potentially unbounded. And now you want to talk to the prover and decide if the input belongs to the language or not. So there's 2 criteria for this, which is one is completeness, where if the input belongs to the language, then there exists this honest prover who's going to convince me to accept this input with high probability. And on the other hand, for soundness, if the input does not belong to the language, for every prover, potentially unbounded and adversarial or malicious or cheating, whatever, however you'd like to call it, for every prover that exists, or rather no such prover can convince me to accept the language with high probability. Yeah. So this is a standard definition of interactive proofs. Now, so interactive proofs have been very widely used for delegation tasks themselves. So this is delegation is the general theme of outsourcing computation to a prover, and then checking if the results of the computation are correct by interactively placing the burden on the prover, on the entity which computes this, placing the burden on it to prove that its results are correct, or rather use interactive proof to verify its correctness. And these delegation protocols have been ubiquitous in like multiple areas of PCS, like just computing languages themselves in NC, or property testing of NC languages, and going on and on. Like this, there's this model for interactive proofs of delegating agnostic learning by Goldwasser, Rothblum, Shafer, and Yehudayoff. And the difference between the couple of problems I've mentioned and the agnostic learning setting is the decision versus search, where in the learning setting, you want to output a hypothesis. So it's a search problem in this sense. And an important criteria for delegation protocols is that they're doubly efficient, where the honest prover is also an efficient algorithm. But then you would ask, you have an efficient verifier and an efficient prover. Why can't the verifier do everything the prover does on its own? So in this setting, we want the verifier to be really efficient, like highly efficient. For example, the delegation protocol for languages in NC, the honest prover runs in polynomial time, whereas the verifier runs in near linear time. I mean, just to remind you, like any language in NC, you want to compute it on its own, you would require, if you're given a circuit and you want to compute it, you would require polynomial time already. And one more point which I want to make clearer here is that for the soundness criterion, your adversary could be unbounded still. The honest prover is efficient, verifier highly efficient, malicious prover still unbounded. Yeah. So I'll make the details of the interactive proof for agnostic learning more clearer. Maybe this will help understand what I mean by this. So again, you have an input function f, which you want to learn with respect to your underlying class C. And an interactive proof here for learning is that you have verifier, which gets, so there's one notion where you want to improve this qualitatively, where you have random example access to the underlying input, and the prover has query access. And the verifier delegates the learning computation to the prover, using which you output a hypothesis H. So qualitativeness here comes from the fact that the verifier has random example access and the prover has query access. And so again, to repeat, completeness here would mean that there exists a prover, P star, such that the output of this interaction is a hypothesis, which is good with very high probability. And what do I mean by good? It's that the error is at most opt plus epsilon with high probability. In the soundness case, for every unbounded prover, the likelihood that your verifier outputs a bad hypothesis is very small. So you either output a good hypothesis or you just say you're lying, I'll just reject you. And another setting here is the quantitative one, where the verifier could also have query access. But in this case, you want the verifier to use much fewer queries. And the prover has, if you use Q queries, the verifier uses much fewer queries. One can say the same things about random examples as well. So there's a qualitative axis where qualitative difference, where on one hand, your verifier is highly efficient, but also it uses only random examples, but the prover uses queries. Whereas in this case, both use only queries or random examples. Yeah. And the completeness and soundness remain the same.
Maybe you said this already, but this verifier, is it important whether we have access to randomness or not?
Yeah, it's so interactive proofs typically you give randomness.
Yeah. Yes. So, but because I was thinking it's not a priori not clear, like if I have access to random examples, then maybe sort of that would be all the randomness. Clearly, if I want to probe, then it's clear that I also need randomness. But I should think of randomness might be useful for all kinds of different.
Yeah. So if the model is clear, like, is there any questions about this? Anyone? All right, so I'll just move on then. So one question is why do we consider agnostic learning in this setting? And can we just have PAC verification for the standard setting itself? And in this case, the model it's not it just trivializes, because the learner can just send you the hypothesis, and now you can draw some examples and their labels and make an empirical estimate for how close your hypothesis is from the original function. And using a Chernoff bound, you can easily differentiate between a good hypothesis and a bad hypothesis. So this model becomes a bit easy in this case. Or I mean, all realizable learners can be verified in this sense. If you send a hypothesis, then using 1/epsilon² many samples, you can check if it's close or far away. But in agnostic learning, this value of opt is very hard to estimate, because it is over all possible functions. You want to minimize the distance between the underlying function and your target class. So it's very hard to estimate this on your own, and agnostic learning certainly makes more sense in this setting. Yeah. So now that we have set up the model, I'll just explain our main results here. So we prove PAC verification protocols for classes that are fundamental to the study of learning theory. One is the heavy Fourier characters of a Boolean function. And next we look at constant depth circuits with and, or, and parity gates. This is AC02. And then K-Juntas. I'll go over this more and more in detail individually. Maybe I won't talk about K-Juntas for now, and if we have time later, we can come to that. And then we also show that, in some sense, double efficiency is required for this model. Like if you give an unbounded honest prover instead of an efficient one, the model again becomes trivial. Yeah, you can even verify learners for p-poly using like 1/epsilon many samples. So yeah, in this case, you can verify learners for like even p-poly using very few samples if you have an unbounded honest prover. So yeah, in some sense, this denotes that like you would like to construct these protocols while they're motivated by a real world setting. That double efficiency implies that, like in the real world, even your server you're delegating the learning to has bounded computation. So it's trying to capture that. In the learning verification setting, it's also, even theoretically, like to make it non-trivial, you need double efficiency.
Is this easy to see that it trivializes, or are you going to tell us about it?
Yeah, I'll tell you about this. It's not straightforward, but also it uses one or two ideas. We can get there. Yeah. And for the first one, I'll just make a very quick recap of Fourier analysis of Boolean functions. So you have Boolean function f from 0, 1 to the n to -1 + 1. So I'll just switch to -1 plus 1 here, which is the Fourier basis. And you express this as a function over the reals as follows, where f of x is for every u, 0, 1 to the n, you express it f hat a few times chi u of x, where chi u of x is -1. The dot product of u and x. And like one of the first results which we learn in this area is the Parseval's theorem, which is that for any Boolean valued function, the squared sum of all the Fourier coefficients is exactly equal to 1. And in particular, when you look at heavy coefficients, what I mean by this is that a Fourier coefficient is heavy if its value is at least tau. So I'll call this set as tau heavy coefficients, f hat of larger than tau, a set of all Fourier coefficients whose absolute value is larger than tau. And again, by Parseval's theorem, the number of such coefficients is at most 1 over tau squared. So Fourier analysis is ubiquitous in many areas of complexity theory, including learning, lower bounds, error correcting codes, cryptography. There's like thousands of applications of it. In particular, the focus on learning theory here is through the lens of Goldwasser, who show how you can learn for any Boolean function f. You can learn all its tau heavy coefficients using membership query access to f. And this is like one of the basic building blocks in learning theory, which is used to learn multiple classes like decision trees or sparse functions. And so far it's only known to be possible using query access to the function. And the paper which introduced this model on PAC verification for learners. So they asked this question: can we verify learners for can we verify learners which provide all the heavy Fourier coefficients using very few samples? And this is the interactive Goldreich-Levin algorithm, and they show that one can indeed do this using polynomial in n over tau many verifier samples, and the queries which the prover uses is polynomial over in n over tau. So our first result is that we show that the set of tau heavy Fourier coefficients is PAC verifiable, such that the verifier uses just poly 1 over tau many random examples, and the prover uses poly n over tau many queries. So it's a very very sample efficient interactive version of the Goldreich-Levin theorem, because the improvement is independent of the input length. So if tau is say 1 over 1000, then rather you want to learn all the 1 over 1000 heavy Fourier coefficients in the function. Then the number of random examples which you need to verify this is constant, whereas the number of queries is still polynomial in n. So this is an input independent separation. And this is also doubly efficient because the prover essentially runs in the time which is required to run the Goldreich-Levin theorem. While the verifier also runs in poly n over tau time, it uses like significantly fewer samples. And to compare this with GRSY again, so GRSY use poly n over tau many samples, versus in our case it's poly 1 over tau. So yeah, it's like a significant input independent improvement.
Is it clear how it fits the formal setting we had before? I mean, we talked about concept classes and returning hypotheses.
Yeah.
So what is and then the hypothesis being close to. So what is the function here?
So you can generalize that to say you learn like multiple coefficients. Yeah. Instead of saying just like there's one fixed class, you just say, you can just generalize this to say you want to learn all the heavy Fourier coefficients of the function. And typically this is used as a building block in other learning algorithms where there's one fixed class.
Okay, but
Yeah.
so what am I getting from the prover, and what is the notion of success?
So
Like
not
I get a list of coefficients.
you get a list of coefficients, and you want to
Okay.
check if they are heavy or not. Yeah.
And what am I verifying, whether it's the complete list of heavy coefficients? Or?
You could have some light coefficients, but you want all the heavy coefficients with you.
Okay, some extra light ones, that's okay.
That's okay, because it only improves approximation. If you look at the broader setting where you use this as a black box.
And so the epsilon delta thingy, like with
Yeah, one can define epsilon here to be, yeah, so for each so there exists no Fourier coefficient which is too far away from a heavy coefficient in this set. So you don't want to miss a large Fourier coefficient and instead have a light Fourier coefficient which is too far away from this heavy Fourier coefficient. Yeah. And delta is just the confidence probability. So that delta here comes up in the soundness and completeness probabilities. Yeah.
So except with probability delta, my answer is good.
Yeah.
And goodness is measured. There's some epsilon fudge
With the Fourier
with
coefficient.
respect to heaviness or not.
Yeah, exactly.
Okay.
Yeah. So now next we talk about learning constant depth circuits, which are, and here we focus on AC0 parity circuits, which are polynomial size, constant depth, and unbounded fan-in circuits with AND, OR, and parity gates. So these form frontier of efficient learnability, like so Carmozino, Impagliazzo, Cabanets, and Kolkolova show quasi-polynomial learner for AC0 parity over the uniform distribution using membership queries. And a follow-up work of this shows a quasi-polynomial time agnostic learner for AC0 parity using membership queries, but the error is multiplicative. It's polylog n times opt. So the key thing here is that the learning algorithms which are known for this class, realizable as well as agnostic, use this membership queries. So we again show like PAC verification protocols for AC0 parity, where if the opt value is bounded away from 0 for a given function f, then AC0 parity is PAC verifiable, such that it uses quasi-polynomially many random examples. The prover uses quasi-polynomially many queries, and the hypothesis error is polylog n times opt. And as you can see by the parameters, in particular the hypothesis error, can probably surmise that like this protocol builds on the CIKK algorithm itself, and thus it also inherits its parameters, like the fact that the hypothesis error is multiplicative, as well as the requirement that opt is at least larger than 0. Yeah. So for context, again, the only learners known without approver uses membership queries. And even in the realizable setting, learning this with random examples has been a long-standing challenge. We still don't know anything which beats brute force using random examples. And moreover, in the agnostic setting, so efficient agnostic learners for AC02 using random examples is believed to be hard, assuming well-known cryptographic conjectures like learning parities with noise, hardness of learning parities with noise. So now, yeah, so without a prover, this class has shown a lot of resistance towards learning using random examples. But suddenly, if you want to verify this, you can actually do so using quasi-polynomial random examples. So yeah, there's like a gap between verification and actual learning in a significant way once again.
Maybe this question is coming a bit too late, or maybe it's coming too early. One parameter, I guess, that people play with that you didn't talk about, like proper versus improper. From the prover, am I always getting like an honest guy inside my console transfer? Would it even be meaningful to talk about, getting some other beast back that is not in the?
Yeah, I mean, that's a good question. I didn't mention it earlier, but for the Fourier setting, you're just getting the Fourier coefficients. There's no proper or improper there. For AC0 parity, it is an improper learner.
Oh,
yeah, this is again inherent from CIKK itself.
So what is the object that I get?
An NC2 circuit. NC2 with like threshold gates on top. Like yeah, it has a lot involved. But anyways, yeah, NC2. It's at least NC2. Yeah, and yeah, so it's an improper learner in this case. Yeah. And yeah, so I have time for to mention this result as well. So if you have an unbounded prover, then we can even show we can go to the distribution free setting, which is the most general case where the examples come from any arbitrary but fixed distribution, and you're supposed to output a hypothesis with error opt with respect to distribution B plus epsilon. And if you have an unbounded prover, honest prover, then even p-poly is fact verifiable using in polynomial time and using 1 over epsilon random examples. And even this is possible in a distribution free sense as well. For context, if you just want to learn p-poly using random examples or even membership queries, there are assuming standard cryptographic primitives like pseudo-random functions or one-way functions, pseudo-random function generators or one-way functions. This is believed to be hard.
Basically, because otherwise I would learn the pseudo-random function
Yeah.
and be able to do all kinds of things.
Yeah, exactly. Yeah. If you have pseudo-random functions in p-poly, then if you can learn p-poly, then you can actually distinguish. If you get a hypothesis for the underlying function, you can distinguish between this and a random function, because for random function, you can never do this. Yeah. And I'll mention a very quick overview of techniques for now. For the interactive Goldwasser-Levin theorem, we design a new interactive proof to learn Fourier coefficients, where firstly, the verifier actually uses queries and uses poly 1 over tau many queries. And for this, the prover is crucially used to help the verifier figure out what the coefficients are. And next, we introduce this new general query to sample reduction framework, the setting of PAC verification, where if you have a PAC verifier where the verifier uses queries, then you can use the prover to somehow answer these queries beforehand and just do the same thing using random examples itself. So any PAC verification protocol where the verifier uses queries can be replaced the PAC verification protocol where the verifier uses random examples. But although it is necessary that the prover uses queries, but yeah, you can still make the query to sample reduction framework here. And for this to work, the query construction algorithm of the learner needs to satisfy certain properties, which I'll hopefully try to go in more detail after this. And for AC0 parity, it builds on CIKK 17 crucially, which in turn uses techniques from pseudo-randomness. In particular, the CIKK learning algorithm is nothing but the Nissan-Wigderson reconstruction algorithm. So here we show how we can generalize this query to sample reduction framework to fit the queries made in the Nissan-Wigderson reconstruction algorithm as well. And this requires like an analysis of the query pattern and the distribution of the queries inside. And for the last setting, the last result, which is on p-poly. So we treat agnostic learning itself as a decision problem in NC, but of exponential size. Now, once we have this, we can use an off-the-shelf delegation protocol for NC languages, say the ones from GKR, which is Goldwasser, Rothblum. And we use, this is a decision problem. So we have reduced the task of verifying an agnostic learner to the task of verifying whether this decision problem has been computed properly. And since the problem is computable in exponential size, and we're delegating the exponential size computation to the prover, that's where the unbounded honest prover comes into picture. And then you can do this using very few samples on one side. And finally, I have a few open questions, which is that for AC0 parity, we have a multiplicative fact approximation in the hypothesis. Can we do any better and just get an additive approximation? And I haven't spoken much about the query to sample reduction framework, but so far we only used it to show two protocols, but there's a lot left to do in understanding how far we can go and what we can't do with this. And finally, personally, I feel the PAC-verification framework, the fact that so far it only works for agnostic learning, means that somehow it's not capturing realizable learning, which is, it seems to be trivial. By the same time, is there like a modification of the model, which can also capture verification for realizable learning, which is also quite relevant. And yeah, I think I'll end my talk here. Yeah, thanks a lot for listening, everyone. Yeah. Do you have any questions?
For the second half.
Okay, cool. Thanks for
Thanks a lot.
Yeah.
So are we taking a break?
Mhm.
Or yeah, so we're taking a break now.
Okay, so now we're back after the break, and Ina will tell us some more about the proof or details.
Thanks. Are there any questions about the model itself? No? Okay, cool. Yeah, I'll just try to explain the proof of the PAC-verification protocol for high Fourier coefficients.
I guess I have one question actually.
Yeah, sure. Yeah.
I mean, I could view this heavy Fourier coefficient business. I mean, is it true even that I could just view it as you return to me a function that happens to be the heavy Fourier coefficient, period? Like in some sense a truncated Fourier representation.
Yeah, so that's
And
another
would that
perspective.
actually be like but that wouldn't be an approximation necessarily because
So you still have to
it's not
define
even a Boolean function or anything, right?
you still have to define an approximation there, and
Yeah.
it comes to the same thing, which is yeah, you want your Fourier coefficients to be as close as possible to the actual Fourier coefficients.
But if I think I just take those heavy Fourier coefficients, that's a function, right?
Mhm.
With the Fourier representation, and I could take that and say that how well does that function approximate the function that I really wanted? But I guess the problem is my original function might have been Boolean, and in general,
Yeah,
if I take a Fourier representation, just truncate it, then I will get something that is
yeah,
anything real value.
yeah. You could get, I mean, you could use some tricks on top of that, like you could take a sine function on top of that.
Yeah.
But then this you go further away from what you actually want. This is more, if you're using this as a black box.
We should really think about the Fourier coefficient because that's what we want.
Yeah, exactly. Yeah. Yeah. Right.
Are those okay?
Let me try. This one.
Okay, okay.
So is this visible?
Yeah, yeah, up to there, yes,
to here.
yes. And I can always turn a little bit too.
Oh, that's fine. Thanks. So the goal is to learn set of all u such that the absolute value is at least tau. Just call this tau itself. Now, it would be instructive to actually quickly go over the Goldwasser algorithm itself. Which is, so you start with the root with the set of all Fourier coefficients possible, which is u 0 1 to the n, and you take the square sum. Also, like, yeah, please feel free to stop me at any point of time and ask me questions. So, this way. So here you look at the all possible coefficients and the squared sum. And of course, by Parseval theorem, this is equal to 1, since f is a Boolean valued function. Next, we look at next layer, where here you look at the squared sum u in 0 1 to the n, such that the first bit is set to 0. In this case, the first bit is set to 1. Then you continue this, so on and so forth. Here u1, u2 equals 0 0, u1, u2 equals 1 1. But if we do, and we do this for n layers. At the end, you get the individual vectors at the bottom, where all u1 to un is set. But now, obviously, this is going to take 2 to the n. You're going to end up looking at all possible sets here. So to make this like polynomial size, we actually use a property of the Fourier coefficients, which is that at each step we truncate the path, or like we just like, so in other words, when I'm making this branch, I'll check whether the estimate of the squared sum of the Fourier coefficients of this node is larger than, say, tau squared over 4, tau squared over 2 here. And if not, suppose this was less than tau squared over 2 here, the sum, it does not go there at all. And by doing this, what happens is that, again, at each layer, I use Parseval's theorem to see that there's at most 4 over tau squared. Sorry, 2 over tau squared, many such buckets. And by the end, you do end up, you have invariant that you had order of 1 over tau squared many nodes at every single layer. But now the next question arises, how do I estimate this? Which is not something I'll go into detail with, but you can use this, you can use a membership query to do this. In particular, I can just write the formula. So u 0 1 to the n. Say, for example, it's just you look at the first two, you set u1 up to ui, then you, this is set to say some A, and this would be what is the expectation of said 0, 1 to the n minus I.
The first term f of y comma z.
Sorry. Yeah, I'm just give me a second. Yeah.
Oh no, I see you different.
I just stitch them together.
Yeah, I see.
So it's just yeah. So you pick a random example and check this, and then you flip the first few bits and make a membership query and check this, and you can take a bunch of estimates to figure out what the sum is. So your prefix U1 to UI to A, you look at vectors with the fixed prefix, and you want to take the square sums here. Yeah. I mean, anyways, this is not very important for us. I just wanted to mention this. So, because we're not actually going to use this anyway. Yeah. I just want to say that there is a way of estimating. Given if you have a fixed prefix and you want to estimate the squared sum of the Fourier coefficients with a fixed prefix, you can do that with one membership query. For one example, like you can do this one membership query, but you need to do this multiple times to get a good estimate. And you do this at each node. And since there are poly n over tau many nodes, you end up making poly n over tau many membership queries. That's the takeaway from this. Yeah. Yeah. Now, is this fine as like a high level thing? Yeah. So going on. So now I want to make this poly 1 over tau many queries, right? So how do I end up just making that? So I just truncate somewhere in between here, just stop it here. But then, as in like I just stop at depth, say log order of log 1 over tau.
So yeah, so maybe this is not. I'm just thinking about the like chi u of y and chi u of y prime. Sort of the dimensions. Doesn't chi u expect like a bit vector length n?
Yeah, I guess that would be
somehow.
Yeah. So that would be right. This would be some S, which is a subset of the first items. Yeah. Yeah. So you fixed this prefix, and the subset of this which is set to ones. See, there's a subset of this. Yeah. So now at this depth, log of 1 over tau. Say I just truncate this as like a thought experiment. But now at every node at this layer, the issue is it has a lot of Fourier coefficients. And also at each node, I could have multiple heavy Fourier coefficients. So I can't really figure out which ones these are. So the reason why they Goldwasser go all the way to the bottom of depth n is because at the end, each node contains exactly one element. So now you know which one this is. But if you just stop somewhere in between, then your node could have multiple heavy elements. I mean, at least I don't see how one could figure out the heavy ones given this. So we need to use something else to build on this. So at this stage,
Actually, there's another parameter that we didn't talk about,
Mhm.
because you said there are, having some light parameters is also okay.
so I have
You said having some light parameters is also okay.
some light Fourier coefficient.
Some light Fourier coefficient, but
Yeah.
that's sort of, but then, I can be stupid to you and I give you all the Fourier coefficients, and I'm definitely hitting both the heavy ones and the light ones. So there's some threshold. on
Yeah, I'm
how
just going
many
to
you
ask
want.
for 1 over tau squared net coefficients.
Okay.
Because I know like this, it should
Okay,
contain.
that's, yeah, right, that's your bone. They could be way fewer, but you're not gonna,
Yeah.
Okay.
Like the malicious prover here, if you think of it, like if it sends me a coefficient, I can figure out its Fourier coefficient value, right? Because so any Fourier coefficient value at part of u is just the expectation 0, 1 to the n f of x times, so I want to call this u, sorry. Yeah, x chi u of x.
okay.
So I can estimate this myself. So the only way a malicious prover can try to cheat is by skipping a heavy Fourier coefficient.
Thanks, yeah, makes sense.
So our first idea here is to use, instead of splitting here on the basis of fixed coordinates, we just use random vectors sampled from 0, 1 to the n for S, which is large enough. And I'll mention what S is. And then, so each node is just the set of all u. I mean, I guess this is the set of all u anyways. So this is the set of all u such that u comma r1 equals 1. And this is such that u comma r1 equals 0. And the depth is now S. In particular, at the bottom, I have 2 to the S, many such nodes, where this one would be u such that u comma r1 equals say a1. Or let me just call this 0. U comma rs equals 0. And again here, so on and so forth. You will have this for every, so here a is equal to 0, but then 0 to the s. Then you have a1 up to a2 to the s here. For each setting of a, you have one node. So this is how I divide my tree now. So in order to analyze this, so I'll just make some definitions here. So I'll define V naught. And I'll first define VA, the set of all u for every a in 0, 1 to the s. VA is set of all u such that u comma ri is ai for all I in s. And in particular, find V naught as as a set where the dot product of u comma ri is 0 for every u in that. But if you think of it, V naught is nothing but the orthogonal space is orthogonal to span R1 to Rs. And each VA can be, and thus we can also define for every H in VA, VA is defined as V0 plus H. So you have a partition of a set of vectors into 2 to the s many cosets of the space V0, but these are nothing but affine shifts of the space V0. So each of them forms a coset in this sense. Is this clear? So, okay, my first claim now with this is that if S is chosen to be large enough, then so each such VA will have at most one of the heavy Fourier coefficients. And this is just, so write this clearly, for S in at least some order now we have that each VA has at most one U from and this just comes via like a probabilistic method argument. Like you see that like you fix VA and you take any two vectors, the probability that they both are in this is 1 over 2 to the s. And then if s is chosen large enough so that you take the union bound over all possible combinations of the vectors from f hat of tau, then you see that for s large enough, each such coset has at most one heavy character from f hat of tau. Does this make sense? It's just like the standard union bound based probabilistic method argument. Yeah. All right. So now, given this, so now we have reduced the task to the fact that there's 2 to the s such cosets, and since by a random choice of the splitter at each level, we are assured that each such coset has at most one heavy coefficient. So now all we need to do is figure out this heavy coefficient from the set. Of course, this is easier said than done because there are multiple coefficients here, but we know that there's at most one heavy coefficient with high probability. So to do this, we for each VA, for each lemma, do that for each VA, say gamma star, another U star is the coefficient character rather with the highest coefficient. Then So, yeah, the next lemma is that for any such coset where which is guaranteed to have at most one heavy Fourier coefficient, which is used like coefficient associated, the character associated with the coefficient is U star, then the value or the coefficient of U star, which is f hat of U star, can be estimated with respect to the fourth norm of the Fourier coefficients in the space. Right? The statement seems like a handful. I'll try to unpack it better. So the underlying thing, what I want to say here is that the maximum value of the Fourier coefficient in a vector space is very close to the fourth norm of the Fourier coefficient of the vector space. And on one hand, the proof of this that so we just firstly you see that f hat of U star to the 4 is at most of f hat of U to the 4 where U belongs to V. This just holds trivially because this is just one of the coefficients in index. On the other hand, this one can be split into f hat of U star to the 4 plus hat of U, some of this, U belong to VA, U not equal to U star. And since we know that each of these is at most tau, we can just replace this by f hat of U star. This is not epsilon, so it should be tau. Star to the 4 plus each of these at most tau, this would be at most tau to the 4. And now just taking 4th root on every side just gives us expression. In other words, we have that f hat U star to the 4 is at most taking the 4th root everywhere.
And the 4 is from the claim.
Sorry?
And the 4 is from the
4
claim.
is just from
From the Ah,
Oh, 4 is not from this
No.
claim. Sorry,
What
4
is
is not.
the
4 nothing
yeah,
to do
why
with it.
4?
Why 4
Yeah,
in that case?
and then 2 or whatever else you want.
Yeah, because we can estimate the 4th. I'll show how to estimate the 4th
Okay,
norm
okay.
using membership theory.
Okay.
Oh, okay.
Yeah,
So
this one can say for multiple things. Yeah.
so we didn't show that some of the 4th guys is tau to the 4, or when did that come up? I missed that, I think.
Sorry, what? Oh, this one.
Just because each single
Each
one
one is at most tau.
most tau.
Each one is at most tau.
Yeah, this is the guarantee we have
Right,
from
yeah,
the
yeah.
vector
Oh.
space. Yeah.
Yeah, but why is it only 1 tau then? I'm missing something.
Oh, right, it's, you have the sum,
What do you mean? Sorry.
is each one at most tau, but
Each
then
one
you
is at
have,
most tau,
but
yeah.
then you have many of them?
You're some lots of them.
I guess, I mean, we can even take like you're summing lots of them, but each single one of them is at most tau, right?
Mhm.
So you can think of this tau times f hat of U the whole cube and take tau outside.
And then the rest is,
And the rest is maybe I can
Or you're gonna but do you know anything about if you could do the squares, I guess.
so you would get tau squared
you can
times
also do the
something which is
square, I
less than
guess.
1.
Maybe that's probably better, yeah. So you can think of it as tau squared
Okay,
times Yeah.
And this and then parseable.
This is at most one, so this would be tau squared, and this would be square root of tau. Yeah, I think this is what we have in the. Thanks.
Okay.
And yeah, I mean, the valid question is why the fourth power, but that's what we can estimate now, which is the next claim. Yeah. Which is that.
Also, one more question.
Yeah.
Sum of the j squares is 1.
Yeah.
And they're all, I mean, because they're squares, they're non-negative.
Yeah.
So they have to be smaller than 1. So can you not just say that that guy over there is just 1? The sum of the fourth guys. But maybe tau is small, or what? I'm really confused with
Tau is small,
Tau is small.
Tau is small, yeah.
Yeah. Yeah, tau is between 0 and.
Oh,
right?
okay.
Yeah, so, and now, so, yeah. Since we can relate the max coefficient to the fourth power, and if I show a way of estimating the fourth power, I can, for each vector space, I can estimate the max value. And the way to do that is, so for any such VA, which I also call as V0 plus H, for some arbitrary representative of the coset, we have that sum of that of U before S belongs to V0 plus H is this is the largest expression. So what part of the board can we see here?
I can just move it a bit, you can see everything. Yep.
So the lemma is at the fourth power of any such vector space or any such coset or affine space, however you'd like to call it, can be computed by taking the expectation or xyz from 0, 1 to n and w sample from V0 complement, which is nothing but the span of the random span which you have chosen, and the expected value of f of x and f of y and f of z times the sum of all this times chi h of w. Now this sounds like a lot, so I won't go through the calculations per se, but I'll give like a quick intuition here, which is that so compute this to the fourth. So one can think of this. So S belongs to V0 plus H as the sum over all S. can just immediately replace this. And in particular, this would mean to say since we are working over F2, we want to say S plus H belongs to B naught. But so this is a well-known thing in Fourier analysis. Like there's even like an expression for this in Randall's book, as in the 3rd chapter, I think, where you can represent this indicator of this with respect to the orthogonal space. So you can check if a given vector is in your space by seeing if it matches the constraints in its orthogonal space. And that's exactly what we are doing here. In particular, this is the reason why we get XH of W here. Because you're looking at a vector from the orthogonal space. And you want to check if S plus H belongs to V naught by computing its parity with a vector in its orthogonal space. Does that make sense at all? So how do I check that S plus H belongs to V naught? I'll check it by computing the dot product of S plus H with every vector that forms the basis of V naught complement, or V naught orthogonal complement. But yeah, but doing this would involve just taking a vector from the complement space and computing its dot product. And in particular, its parity with respect to W and H itself. So that's where this crops up, and that's where this also crops up. And the rest are just to eliminate X, Y, and Z, so that we end up getting this thing overall.
I guess it becomes clear if you see the entire proof, but the equality you wrote there.
Yeah.
This is also true for powers of 2. It's true for any power.
Yeah, so we need to get rid of the other things here.
And the other things go away if you have the 4th power.
Yeah.
Oh, okay.
Yeah.
Go away.
Yeah.
What other thing?
So you need to take expectation of f of x and f of so when you take the expectation of 2 different parities, since they have the same probability, and you have -1 and +1, the expectation just becomes 0. So that part goes away.
Okay.
Yeah, I mean, it'd be clear if I go through the calculations of this, but
Okay.
that would take just gory
Okay.
details at that stage. Yeah.
Okay.
But the main idea is coming from this. Yeah. So these are like the key technical ingredients for the first step of this algorithm, where you can use the 4th power. You can estimate the 4th power using 3 random examples and 1 membership query. And using that, you can estimate the highest Fourier coefficient value of each space. So that's my algorithm now. Can I erase any of this? Yeah, I think I'll just erase this is fine, I think. The key takeaway here is that we can estimate the 4th power. Yeah. So I'll keep this one for the future. For the rest, I'll erase. Yeah. When do I need to stop, by the way?
I don't know, like, we usually go for like an hour afterwards.
Just
Yeah.
let me know when I have to stop.
Yeah, okay.
Yeah. So at this stage, so we have an algorithm now to estimate the highest Fourier coefficient value in each vector space. How do I do that? I just pick R1 to Rs. And then I have the 2 to the S many vector spaces at the bottom. And for each one of them, I'll estimate the highest Fourier coefficient value. So unlike Goldwasser, where I make the estimate at each node, so I just pick all the random vectors here and make a one-shot estimate at the end. The 2 to the S many STH. And since 2 to the S is also poly 1 over tau, we're fine. We are ending up making poly 1 over tau many membership queries and estimating the highest Fourier coefficient value in each vector space, right? But now you'll ask, you just estimate the highest Fourier coefficient value. There's not really learning because you don't know what character it corresponds to. So this is where the prover comes in. So the prover now sends a purported value of the heavy Fourier coefficient to the verifier. And the verifier, firstly, computes the Fourier coefficient for each. So when I say t here, t is nothing but say 1 over tau squared. So it sends all the 1 over tau squared Fourier coefficient, Fourier characters to you, computes the Fourier coefficient for each u belonging to lambda tau of t, and then it uses this algorithm which I mentioned earlier to compute the set of heavy Fourier coefficient, heavy Fourier coefficients. Can I use another pen?
Mhm. Okay.
Be a little bit careful with the font size also if we want the video to be.
Yeah,
Yeah, is this visible?
it's
Yeah, but
visible,
you're
just this.
using a much smaller font size now.
I see. I can rewrite this. So computes every u in lambda prime t. Next. Computes everyone. Using earlier algorithm, and then it checks if the lowest value, which it has computed here, the lowest value which it receives from the prover.
Sorry, what is the prover sending?
Yeah, so the prover is sending a purported list of characters. So it just sends, say you, I'll
Which
just call it
are
V1.
supposedly the ones with highest.
Yes, they're supposedly the ones with the highest Fourier coefficients.
Okay,
Prover sends this.
and it sends 1 over t squared of them,
Yes, exactly 1 over tau squared.
tau squared.
Yeah.
And
Exactly 1 over tau squared of them.
okay,
And the verifier has computed its own set of heavy Fourier coefficient values. So now, and the crucial thing is that the prover sends this in descending order. So the verifier looks at the smallest coefficient that's computed from this list and checks if there is one of the spaces which does not have any of these things, and this value is way off the max value in that space. It means that the prover has not sent the heaviest value and has lied there. So to repeat, so the verifier has looks if there exists VA such that C tilde lambda is the smallest value it has estimated from the prover's list.
which should be corresponding to the last one. Or
It corresponds to the last one.
But
because
what
the
does it
descending order.
matter? I mean, if I did, once I get the characters, I can compute these values.
Exactly. So the prover could be lying.
Yeah, but I mean, I don't care whether the prover gives me a sorted list or something. I get a bunch of characters.
Yeah,
Can I not compute the weights myself? And now once I have the weights, I look at the smallest weight. And I look at all the estimates from before, and if there's a heavy subspace that is like way heavier than the smallest thing, I think no way you're cheating me.
yeah, so the reason for this is that this means that we can only look at the last value.
For
And-
efficiency purposes.
Yeah, we only can, not efficiency purposes. So, I mean, okay, what this means is that if you look at the last value, I don't need to worry about anything before that. Because if the prover has lied on one of the values
Yeah.
and everything is descending, then the last value is obviously far away. If even something in between is far away.
But you need to check that it's descending anyway. You need to compute.
Sure, we can ensure that it's descending, fine.
But then you're shaking it anyway, so why can't I?
So this also helps us ensure that this is the actual list. It is, we can compare it to the largest values which we have obtained in some sense. So we have our own list of large values,
Mhm.
but we don't know which ones each correspond to.
Right, yeah,
So this also helps us like fix these. What the prover is sending is close to whatever these things are, which we have computed on our own.
okay. But it doesn't, it's not more efficient, like if you just compute the value and order it yourself, it would be just the same thing.
Yeah, so, but it's not tagged to the Fourier coefficients which have been sent by the prover. Does that make sense?
Wait, say that again?
So the prover sends a list of
Uh-huh.
coefficients to us,
Right.
right?
Uh-huh.
Which are purported to be the largest coefficients. And now we don't know if which values these correspond to, which we have computed.
Uh-huh.
No, but you talked about before that once I get a coefficient, I will just do a bunch of, a few random samples and or are these queries? Is that the problem? Like we discussed before that I could, if you just give me a Fourier coefficient, I will figure out the heaviness of it on my own.
Yeah, but the prover could have missed something.
Yeah.
Yeah. So
I
sure.
totally agree, but if you give me a bunch of, like, I don't care about how you order V1 to VT. Like, I couldn't care less. I'll just thank you for these coefficients. Good. I'll now compute the weights of these myself. Thank you very much. I'll sort them myself. And now I'll look at my subspace estimates and now I can tell if you're off. Like, because even if you're telling this the prover to give it to me in sorted order, I guess I still have to check sortedness in that case. I mean, it's a very minor point, it's just a little bit confusing. Maybe we should get stuck on it.
Yeah, that makes sense. Because I was thinking like when the prover sends these characters, you want to associate these characters with what you have. But that's not really necessary. All I care is the list of heavy coefficients. All I care about. So I can just make the descending order myself. That makes sense, but I need to double check this once.
How do you
Yeah.
check then if what you were gonna write now? You look at the one with the
Look
lowest?
at the lowest
Uh-huh.
one and just check if there is a VA which does not contain this. And there exists some other value in this which is way higher than this. There exists VA such that, say, omega A is the max value. Within VA.
What you estimated, that's like your estimate
Estimated from this.
from this, okay.
Yeah. If such that if there exists a VA such that VA is the max value, and
now I guess you want it to be none of the VIs you receive. I mean, it could be V1 or V2 also. It's fine.
VA intersection lambda T is null, and C hat lambda is much
Larger.
yeah, C hat
Oh,
lambda
so yeah,
much
so smaller than
Yeah.
your WA.
Yeah, W A minus is larger than say 2 tau over 3.
Mhm.
In this case, it means that you've
Miss.
Unless some other earlier VI lives there, right?
No, but
Yeah.
intersection is empty.
Intersection is empty.
Oh, with the whole lambda,
Yeah.
okay, good,
Yeah.
yes,
Yes.
yeah. Yes.
So this is, crucial condition here as well. So now using this, we can check if the prover has sent all the right
Mm,
characters and the values are close enough.
mhm.
So this is the entire protocol. Now it uses poly 1/tau many queries. Because we are only running this for poly 1/tau many subspaces. And then that's all. That's the only queries which we are making. We're making some random samples to compute these estimates, but that's very small. Yeah.
Mhm,
Again, poly 1/tau many samples.
mhm,
So is this fine? Is this clear?
mhm.
This is the algorithm overall. But now I had promised that, in fact, this algorithm would use samples and not queries. So for that, we have this general framework of transforming queries in the PAC verification setting to random examples,
Mhm.
which is that I think I'll just go this quickly. So a couple of things to observe here for this. Firstly, the membership queries made come from this estimate. Yeah. And each of them has, if you look at the marginal distribution of each of these queries, they're all uniformly random. And secondly, it's all non-active. Which means that all these queries are generated at one shot in the very beginning. So firstly, what I want to say is that replacing queries with samples in the standard setting is hard. Because as we talked earlier, there are actual separations for many classes. Or rather, for this one class at least, and others we don't know. We haven't actually proved anything better than brute force. But in any case, so given a prover, we can actually do that because we have fixed the fact that these are uniformly random marginals and they're non-adaptive. So what I'll do now is that I'll pick a uniformly random vector as a verifier. So verifier picks. I used R and picks a random example, W from F of W. And what it does is that it picks a random location in its query set. So the reason why non-adaptivity helps is that it generates all its queries beforehand. And or rather it has the capability of generating all its queries beforehand. So it picks a random position in its query set and fixes that to be W. And based on this W, it builds the rest of the queries. So the crucial thing here is embeddability. Just that for every W, if W is picked as a random query point, the rest of the query set can be constructed conditioned random query point by J, condition on the J query being equal to W. So embeddability means if you pick any W, if W is placed in a random query point J, the rest of the query set can be constructed conditioned on the fact that this query is W. To make it more concrete here, suppose I picked this as my random query, as a point of my random query, then I'm all right, because this is a random example. I can just set this to W, and the rest, I guess there's a W here already. Let me call this W hat. If I set this as W hat, then I can build the rest of the query set easily based on this being W hat, because I just need to pick two random vectors here and take the sum of everything with another W from this vector space. On the other hand, if this was set to W hat, then I can pick X, Y, Z uniformly at random and set R1 to RS here to be equal to, and also pick R1 to RS minus 1 uniformly at random and set RS as being equal to whatever would help me achieve this as being W hat. In other words, so we know that W is just some BI RI, right? Because W comes from V0 and R1, say R1 to RS is linearly independent. High probability we can ensure that. W is some BI RI. And now I want, so suppose this vector was set to W hat, which means that I want to build the rest of the query set conditioned on X plus Y plus Z plus W equals W hat.
But you're still building the query, like you're still in the query model where you can choose what to query.
Yeah, but
Okay.
I'm going to send all this to the prover.
Okay,
The prover is going to answer everything.
okay.
And since the marginal of each query is the same, it remains uniform. The prover doesn't know whether I fixed the query or it came from the underlying query set. So it is forced to answer every single one of them honestly. Otherwise, it'll get caught.
I see. Okay, so the you will choose have one which you get from the random sampling,
Yeah.
and then the rest you will
Exactly. The rest I'll just send to the
send to the
prover.
prover. Okay.
And the prover has to answer correctly everywhere. Yeah.
Okay.
Yeah.
And it's sufficient with only one? Like,
I'm using, so yeah, so the probability that the prover escapes now is that, so all the prover can do now is hope that wherever it is answering, so okay, so let's say there's Q queries, it'll pick one at random to choose to lie at. The best the prover can hope for is that this query is verifier doesn't check it, because the verifier can only check this. It only knows this value. The probability that the prover gets away with cheating is 1 minus 1 over Q. So you repeat this Q many times. You get to like a constant whatever.
Okay. Oh, nice.
So this is the hiding protocol. You use one random example, use it to build your query set, and ask the prover to answer everything.
Okay.
Yeah. And
Q here is going to be probably 1 over 2.
Q is poly 1 over tau.
Okay.
Yeah. And embeddability, as you see, is very crucial here, that we need to actually hide a random example inside.
Right.
But the rest, this in particular, this the fact that each query is uniformly random marginal, it is used for this construction, but for the CIKK one, we even get rid of this. We use something much more general. Non-adaptivity somehow seems useful now, but I don't know. It's open if one can make this adaptive. Yeah, but embeddability is definitely a crucial aspect for this. So how far we can go with this framework depends on where we can be with the marginals and the non-adaptivity.
So where did you use the uniformly random marginals for the argument?
Oh, the fact that I pick a uniformly random vector.
Okay.
So it means that the prover does not know. So the prover looks at a bunch of queries, and then it just checks for each query. Oh, did this come from the underlying query set, or did the prover, the verifier, pick a uniformly random sample there? But since they're both the same distribution,
Right.
the prover can't do much there.
Okay,
It is forced to
Yes.
answer correctly. With high probability, yeah.
Okay.
Yeah, I guess that's the entire proof and,
Nice.
yeah, we can, I can talk about the CIKK one further if you want, but you also take that offline if anyone's interested, thanks a lot for listening.
Yeah, thanks.
Yeah.
Thank you.
I guess the last bit was a bit too fast, maybe. Anyone's more interested, we can talk about this. It's also like 2 hours, so I can imagine. Yeah.
Okay.
Thank you so much.
Thank you.
Yeah, thanks for this.